Limits of trig functions. Our objective is to find limits involving trig functions. Now, before we talk about special trig limits, let's make a note that if we can, we are always going to try to use substitution. If it's a well-behaved function and it gets where it's going, then substitution will work. So always start with that. Now, often with trig functions, there are some times where substitution won't work. And there are two special trig limits that we want to look out for. Memorize these, know them, and think about using them when substitution doesn't work. We've got the limit as theta approaches 0 of sine theta over theta. That will always equal 1. That can be proven looking at a table of values. Also, the limit as theta goes to 0 of cosine theta minus 1 over theta, that one equals 0. I like to remember it kind of like this because one of them is 1 and one of them is 0. I think of cosine as the one that has an O in it, so it's going to equal 0. Sine is the one that has an I in it like a 1, so it's going to equal 1. Just some helpful memory tricks that often help me. Let's take a look at some examples. Find the limits. The limit as theta approaches 0 of theta times secant theta. Now remember, we always want to use substitution if it works. So let's give that a shot. Theta is going to 0, so I'll plug 0 in for theta. 0 times secant 0. Now, I'm not really familiar with secant, so I like to change it into cosine. So 1 over cosine of 0, and I do know that cosine of 0 is 1, so I'm going to get 0 times 1 over 1, and of course 0 times 1 is simply 0. So that worked out, and we didn't have to do anything special. Limit as theta approaches 0 of 1 minus cosine theta over 2 times sine squared theta. Of course, I'm going to try direct substitution. Can I plug the 0 in here and get an answer that works? Well, I know that sine of 0 equals 0, and 0 squared is 0, so it looks like my denominator is going to be 0. That's not going to work out so well. So we think of some strategies. Now, just because we know these special trig limits that we talked about at first doesn't mean we're always going to have to use them. We have to sometimes be creative and think of our identities that we know for trig functions, such as when I see sine squared theta, it reminds me of the identity sine squared theta plus cosine squared theta equals 1, the Pythagorean identity. So sine squared theta can be changed into 1 minus cosine squared theta. So let's rewrite this limit. Limit as theta goes to 0 of 1 minus cosine theta over 2 times 1 minus cosine squared theta. Now all we did is change it. We didn't get rid of anything, so our denominator is still going to make 0. But now notice that I have a difference of squares right here. This can factor into 1 minus cosine theta times 1 plus cosine theta, and now I have common factors that can divide out. After I divide that out, my limit looks like this. Limit as theta goes to 0 of 1 over 2 times the quantity 1 plus cosine theta. Now that I've divided that bad factor out, I won't get 0 in the denominator most likely. Let's check it out. 1 over 2 times 1 plus cosine of 0. And I know that cosine of 0 is 1, so 1 over 2 times 1 plus 1 is 1 over 4. And that works out. How about the limit as x approaches 0 of tangent x over x? Again, direct substitution I always try first, but I notice I get 0 in the denominator. So let's think about identities that we can use. I know that tangent of x is equivalent to sine of x over cosine of x. And I often prefer to work with sine x and cosine x, especially because of my special trig limits that I know now. So let's see what happens when we rewrite our limit using sine and cosine. Limit as x approaches 0 of sine x over cosine x all over x. I don't usually prefer a complex fraction, so let's rewrite that again. Limit as x approaches 0 of sine x over cosine x. Instead of divided by x, we will say times the reciprocal of x, 1 over x. Now, I still get 0 in the denominator, so it's not like I've made it easier, but what I do notice is that I have a sine x in the numerator and an x in the denominator, and now it's looking more like that special trig limit that we first introduced. So let's do some rearranging. Limit as x approaches 0 of sine x over x times 1 over cosine x. Remember that when we're multiplying fractions, anything in the numerator gets multiplied, anything in the denominator gets multiplied, so it doesn't matter what order that I'm multiplying. Now I'm going to use my limit property to rewrite this product as the limit of one of the factors times the limit of the other factor. And now I remember, because of my special trig limit, that that guy is 1. Remember, the I in the sign makes me think of 1, times, and then using direct substitution over here, 1 over cosine of 0, and cosine of 0 is 1, so that comes out in the end to 1. And that worked out. How about these? Limit as x approaches 0 of 1 minus cosine x over 3x. Now, if I plug in 0 into the denominator, or into the x, excuse me, I get 0 in the denominator. That's not going to work out. Now I notice that this looks very much like my special trig limit that we talked about at the beginning. Well, it is opposite that in the numerator. So what does that mean? Plus, I also have this 3 that's in the way, because that's not in the special trig limit. Now remember, with limit properties, we can take this constant multiple and pull it out of the limit. So that part is an easy fix. 1/3 times the limit as x approaches 0 of 1 minus cosine x over x. Now it's looking closer to our special trig limit, but this looks backwards of what we wrote. How can we turn this around if it's a difference? I can factor out a -1. What does that look like? 1/3 times the limit as x approaches 0 of -1 times cosine x, because now cosine x is positive, minus 1. I factored out a negative, so now positive 1 is -1, all divided by x. And now I do have what that looks like, and of course, that constant multiple, that can easily be factored out. So let's rewrite it. -1/3 times the limit as x goes to 0 of cosine x minus 1 over x. Now this does look exactly like our special trig limit, and we remember that because there's a O in cosine, not an O in sine, that this limit is 0. So -1/3 times 0, and that gives us 0. And we did it. Now, I don't want you to feel like every time you come up with 1 minus cosine x, instead of cosine x minus 1, that we have to go through this extra step of factoring out -1. Because this is a difference, and 0 is 0 either way, we're going to just make a note that this limit is exactly the same as if we just had the limit as theta goes to 0 of 1 minus cosine theta over theta. These are the same. They still are going to give us 0. So instead of having to factor it out every time, whether you get cosine theta minus 1 or 1 minus cosine theta, as long as theta is going to 0, our limit is going to be 0. Now I put these next to each other because I want you to notice the difference in where that extra constant multiple is. Notice in this one that I still get 0 in the denominator, and this looks awfully close to that special trig limit, sine theta over theta as theta goes to 0. However, we have this extra constant multiple, but it's inside the sign. So we cannot just pull it out like we did before. That is a big no-no. We can't take anything out from the inside of the sine function. So how do we deal with that? Now notice the way that we wrote this special trig limit was with theta. It doesn't really matter what we write it with, but what I want you to notice is that theta is here, theta is here, theta is here. It can be x, x, and x. It can be t, t, and t, as long as it's sine of the variable over the same variable and that variable is going to 0, then this limit will equal 1. So being that we can't take the 5x out here, we want to put a 5x down here. Well, can we just do that? Can we just say, write 5 next to that? Well, next to it means multiply. So if I want to multiply the denominator by 5, guess what else we have to do? Multiply the numerator by 5, because 5 over 5 is just equivalent to 1, so essentially we're just multiplying this expression by 1. Now the 5 that we want in the denominator will stay there. This 5 we can pull in front as a constant multiple. So now our limit looks like this. 5 times the limit as x approaches 0 of sine of 5x over 5x. Now this is better, these match, but this doesn't match. Now think about this. We can rename 5x to be just one variable. Let's let t equal 5x and replace the 5x's with t. And let's think about the fact that if x, let's write it like this, if x is going to 0, then 5 times x will also be going to 0. Therefore, I can also replace this with t. T will also be going to 0. So now I'm going to rewrite my limit. 5 limit t approaches 0 of sine of t over t. And now I see that special trig limit right there equals 1 because the sign has an I in it like a 1, and 5 times 1 makes 5. And I've done it. How about this one? Limit as x approaches 0 of x divided by sine x. Well, that looks awfully close to the special trig limit sine x over x. And of course, the x is going to 0. But it's not exactly the same. Well, let's think about this. This expression is equivalent to the limit as x approaches 0 of 1 divided by the reciprocal of that fraction, or sine x over x. Using our limit properties, we can say this is the same as limit as x approaches 0 of 1 divided by limit as x approaches 0 of sine x over x, because we know this limit in the denominator is not 0, and this will make 1 over 1, which equals 1. And we've done it. Now, just to make life a little simpler, we can, instead of having to go through this process every time, just make a note that this special trig limit is the same as the reciprocal limit as theta goes to 0 of x. Oops, I didn't use x in this, so I will use theta. Theta over sine of theta is the same. The reciprocal of 1 is still 1, just like a difference that equals 0 is still going to be the same when we switch it that way. Thanks for watching.